Hey, welcome. Let's get right into it. So the two dot points we're looking at today are comparing induction and deduction and assessing parsimony and how much it's been able to influence the development of science. For these three things, we're going to look at some examples from science history. So first of all, induction and deduction. Um, Both of these are different methods of seeking out new knowledge from old knowledge. Um, Induction takes observations um, makes observations and then makes broad generalizations based on those observations. So we go from observations down to some kind of theory based on those observations. So you could say that I have gone out into the world, I have seen many swans, and they've all been white. All the ones I've seen 50 white swans in the wild. Those are my observations. Therefore, via inductive reasoning, I could say my theory could be that all swans are white. Okay, so you made some observations. From those, you made a theory. The observations are you assume they're correct, but the theory might not be correct. You've seen 50 white swans, but perhaps the 51st swan you see will be a different color. You cannot be sure of that. However, you can, with inductive reasoning, you would give some kind of probability to your theory. You would say, I have traveled all across the whole world. I have seen every swan that everybody has ever known of, and they have all been white. I am pretty sure that every swan in the world is white. You're pretty sure it's still not certain. Deductive reasoning gives you a certain amount of certainty, but it still has its own uncertainties with it. With deductive reasoning, you have theory or theories, and you use those theory to predict observations. So here, your predictions must be correct as long as the theory is correct. So the usual way to say this is something like A is equal to B. That's your first theory or your first assumption. B is equal to C. Therefore, A is equal to C. If the first two statements are correct, then the third must be correct. That is deduction. So some people might say that deductive reasoning is superior then. In reality, both of these have their role in science. For most scientific endeavors, we start with observations. We use inductive reasoning to come up with theories, and then we use deductive reasoning to test those theories with new observations. So it's a continual cycle. And yeah, when you read about famous science in history, you normally only see theory get turned into observations through experimentation. But really, everybody starts with observations first. Nobody starts doing experiments on some system. You know, if you want to study dingoes, you don't design your experiments without having any knowledge or observations of dingoes. You'd go out, you'd sit in your car, you'd look at them, you'd find them, you would study them, and just make lots and lots of observations before trying to come up with theories and then test them. Now, deductive reasoning is good for testing your theories, right? Seeing if they're true. It can also be used to create new theories. So the example of that I'm thinking of is with Einstein's special relativity. So Einstein had two theories, or I shouldn't say theories, but two assumptions he was using. One of which was that all inertial frames of reference are equal. So inertial frames of reference are equal. And his other one was that the speed of light is constant for all observers. Based on these two assumptions, he was able to deduce what is a necessary outcome of those things, which is special relativity, the fact that at different speeds you get time dilation, length contraction, um, mass dilation, that sort of thing. Okay, he used ideas and turned them into observations you'd be able to make, which would be time dilation. An example of inductive reasoning could come from Charles Darwin. He traveled the world making observations of different species in different ecosystems all across the world, and he used his observations to come up with his theory of natural selection. Once he had the theory, it's been tested many times. Lots of other observations have been done in order to test that theory, but Darwin himself started with the observations and created a theory based on his observations, and Wallace as well. Okay, now the next bit, parsimony and Occam's razor. And this part can also sort of be called abductive reasoning sometimes. This is where we use whatever evidence we have and we try to find the best fit for that evidence. Now, what do I mean by best fit? I mean that we want to be able to explain every piece of evidence with the simplest explanation possible. So an example of that would be if you've got some data, right? Yep, you've got a graph, X versus Y, and you have some data like this, right? Now, hopefully you've learned that you should draw a trend line through your data. That's not a very good one, but something like that, yeah? By drawing this trend line, you are saying that the simplest explanation is that the relationship between Y and X is a linear one. An alternative to this could be to draw this line. Now, this line is saying that for some reason, when X is exactly this value here, there is a spike in Y that then disappears again before and after X. And the same thing happens here. Okay, now you could come up with a theory that says why this amount of X and this amount of X causes spikes in Y. But that theory probably has a lot of loops, hoops, and hurdles in it. The more simple explanation is that your measurements when you took this data were slightly off what they were meant to be, and that really this trend line is the correct outcome. In practice, an example of this is Wegener with continental drift. There were some competing theories to explain different phenomena. So one example of that was between, that one looks more like South America, between South America and Africa. Well, I'm not going to be able to draw this very right. The coastlines of the two. There were similar rock formations and fossils found at sites, as Wegener said, as if the two used to be together. There were competing theories such as that it used to be land connecting the two, which has been eroded away by wind and waves, which, just to explain this piece of evidence, both theories seem to fit equally simply, but then later on, when it was found that there were deep trenches under the ocean exactly in the middle of the two land masses as well, plus a whole load of other evidence, the idea of land bridges, in order to make them make sense, they had to tack on more and more different bits to their explanation, whereas Wegener's continental drift fit it very well without needing to add any extra explanation. And one more example of this goes back to Einstein. Einstein's theories came after the discovery that the ether did not exist, or at least the Michelson-Morley experiment showed that the ether wind was not detectable on Earth. Now, Michelson and Morley didn't like the idea that there was no ether. They thought there was an ether, so instead they changed their model to say, well, as the Earth moved, the ether was dragged along with it, so there was no ether wind. You can see that they're tacking on extra bits of explanation into their theory to try and make their theory fit the observation, when really the theory of the ether was wrong and they needed a simpler one to be present instead to explain their experiments better. Okay, in your own projects, you should be using inductive reasoning at first, trying to just observe and see as much of your own systems, whatever you are using to experiment on, as much as possible. Then using deductive reasoning to try to think of what are some observations that should be true if your hypothesis is correct, then to test and learn them. And then once you have your evidence, you then use parsimony, Occam's razor, try to think of what the simplest explanation to explain your data is, and that should hopefully be the correct one.